All right, everybody, we're kind of at the pinnacle of our trigonometry unit now. We're going to be going through we're going to be looking at solving trig equations. So everything that we've been doing up to this point, so simplifying and verifying and doing the unit circle has gotten us ready for this point right here. We're actually going to solve equations that have trig functions in them. So first of all, let's talk about what it means to have a solution to an equation, because if we don't know what that is, it's going to be kind of hard to figure it out no matter what kind of equation you're dealing with. So solutions are values that make the equation true for the variable. So you're looking for values for a variable that make the statement an equality, so equal. So in this case, if we're dealing with trig functions, that means we're going to be looking for angle measurements that make the equation true. We're going to be looking for things for theta or whatever variable they're using to stand for an angle. So that's kind of one thing that's unique about trig functions, is that it's an angle measurement that you're solving for. So if it's an angle, that means we have some choice, right? It could be either in degrees or radians, kind of a personal preference, but also whatever we're doing with it. So if we're going to be able to do some work or be able to solve, we need to think about what that might look like. Now, the idea that it's an angle measurement too kind of leads us to the next thing, and we can talk about this for any equation. How many solutions can equations have? Well, it depends on the equation. So what if you have a quadratic, like a degree 2? Well, a degree 2 could have up to 2 solutions. So it is possible that equations have more than one answer. Is it possible that equations don't have any solutions at all? Think of a parabola. Does a parabola have to cross the x-axis? Well, no, it could not cross at all, which means there would be no solution to that equation as well. Is it possible that an equation could have infinitely many solutions? Well, if you're looking for solving equations, we're talking about things that have multiple possibilities. In angle measurements, that can definitely happen, because in an equation with angles, you're talking about things that are coterminal. So how many angles are coterminal with 30? Well, you can add or subtract 360 as many times as you want to, so there'd be infinitely many solutions unless we restrict the domain. So we're going to spend a fair amount of time over the next couple of parts of this talking about how do we want to write solutions? What kinds of solutions do we want to have? So there's really 3 options. I can make the restrictions so we can do what we call principal values. So we've talked about those before. Principal values are where we restrict the domain so that the inverse would be a function. We'd only have then one solution, one answer that makes that equation true, so only one angle measurement. A lot of people like those because you don't have to worry about anything else. It's just one of them. We're all using the same value instead of the infinitely many option for the coterminals. That's what your calculator is programmed to do. Sometimes we're actually looking for more than one, though, depending on what you're doing with that, and we make a limitation ourselves of what we want to use. So you could say something like 0 to 360, or if you want to do it in radians, it would be 0 to 2 pi. That would be fine too. And remember the difference between the bracket and the parenthesis. You don't need to say 0 and 360. So if we stop just right before 360, then we can just give each answer one time. That's kind of a nice way to look at it, because that's the regular unit circle. Or we could just definitely just talk about, I want all values, which means there are going to be infinitely many of them. So we have to think about how we write those and talk about all the angles that are coterminal. So we have different options, I guess, when we think about how we're going to write those solutions. Okay, so for today, I'm going to bring you back to things you already know how to do. You guys are really good equation solvers. So if we can think about how we solve equations in algebra, in that world, then we're going to be able to deal with it in the trig world just the same. So I'm going to kind of separate these first few as looking at an equation in the algebra land versus trig. So let's talk about this first algebra equation. So if we're looking at that, and we're making sure that we can think about what that looks like. It's a degree 2 equation. So because it's degree 2, we have some strategies that would go along with that. So this is degree 2. How do you solve a second degree equation? Well, we solve that by factoring. So some things to notice about this equation right away is that all the variable is y, so everything is using the same variable, and the highest power it's raised to is a 2. So in algebra land, that means we solve it by factoring, if it's factorable. So what do we do if it's not factorable? What's your backup plan? Well, we can use quadratic formula. So some people prefer to do that anyway because they have trouble with the factoring. So quadratic formula would be the way to go if you're not big into the factoring, or what if it doesn't factor with whole numbers? So you always have that backup plan, but factoring is our strategy. Okay, so if it's factorable, we always want the equation equal to 0 first, so we can use that zero product property, and we break it down into its factors. So what multiplies together to give you that expression? So 2y times y multiplied to get a 1 would be a plus 1, and a -1. Let's talk about where we want each one to go, though, here. I think we want minus in the first one and plus in the second one. Let's double check. Things that multiply to give you a 1 for the last, we know it has to be 1 and 1. If it's a -1 for that last term too, I know the signs have to be opposite. How do you check to be sure that your factors are correct? Well, we have to do the distributive property and see that you get back to that trinomial. The only ones you really need to check though are the insides and outsides, as long as you've picked the numbers correctly, because that's what generates that middle term. So 2 times 1 would be 2. -1 would be that 1 in the middle. So you're going to have to factor to be able to do these. All right, so now where do the solutions come from though? Those are just the factors. Well, if you've got two things multiplied together and your answer is 0, that means one of those two things has to be 0. So I'm going to set them both equal to 0 and I'm going to solve. All right, now I know some of you don't show what I just did in green. You just go right to the solution. You do that solving in your head, and that's okay as long as you know what you're what you're doing with that. But that's where it's coming from. Multiply, these things are multiplied together. The only way to get a 0 for your answer is if one of them is 0. So that means then, in this situation, this was a degree 2, which is a parabola. When you're solving it, then we're looking for the values that make it 0. We got our 2 solutions. Now, let's take a look at what it looks like in trig version. So I want you to compare the equation that's on the right-hand side down the trig column. I want you to see how it's similar and how it's different. So compare and contrast these two equations. So similar-wise, it looks like they have the same coefficients, the same signs, plus or minus. They're both equal to 0. Main difference is instead of writing the y's, I wrote sine of theta. So I replaced the variable with a trig variable, sine of theta. So if you remember back to verifying, we did the same exact thing. If we were trying to solve something or simplify something or verify it and it was too hard, we rewrote it as an algebra thing so we could see what we did or would do. And that's exactly what I did for you here. You know how to solve second degree equations, so I just wrote it in a way that looked more familiar. What I want you to get comfortable with now is that trig is the same equation. It's degree 2, it's equal to 0. I'm going to solve it by factoring. But now instead of y, I'm going to be writing sine. So 2 sine minus 1 and sine of theta plus 1. And again, we do the same strategy. We're going to set each of those equal to 0 and solve. So I'm going to set each of those factors equal to 0, because what makes each part 0, and solve for the variable. So the first one would be when is sine of theta a half? And the second one, when is sine of theta -1? Now, this is where algebra and trig sort of deviate from each other a little bit. In algebra, we would have been done. Those would be the two places where the graph crosses the x-axis. Now we're looking at the places where theta crosses the x-axis, or what angle measurements that's going to happen at. So we're not quite done. We have sine of theta equals a half, sine of theta equals -1. We need to know what angle measurement makes that happen. So think about where in the unit circle is sine of theta equal to a half. All right, so sine of theta is a half at 30 degrees, so that would be one location. Now we need to talk a little bit about solutions. So remember how I said that we could have more than one place, right? Because there's a whole bunch of places that are infinitely or coterminal with 30 degrees, infinitely many of them. So I want to impose a restriction on you so we have something to talk about. So I am going to impose this restriction. We're going to go from 0 to 360. I want you to think of all the places where sine is a half in 0 to 360. Well, 30 degrees is one place. Is there any other place? Or places? Well, where else is sine positive? Besides quadrant 1, which you already gave, how about quadrant 2, right? So what's the 30-degree reference angle in quadrant 2? That would be 150. So we have two places. How about quadrant 3? 330, or quadrant 4, I should say, or 210 in quadrant 3. What about those two? Could those be solutions to that for theta? Well, no, because those are -1/2. That's not the same thing. So quadrant 1 and quadrant 2. So those are the only two places. When is sine equal to -1? Same idea. So that's happening at 270, and that's the only location, just at 270. Now, again, I limited you to 0 to 360. If I just said principal values, how would my answer be different? Well, I would only have on the first sine is a half, I would only have the 30-degree answer, because that would be the one principal value. On the other one, I would only have one value as well. It'd look a little bit different. So I want you to grab your calculator for a second, and we're going to do a little bit of work here. What if you just totally forget that sine of 30 degrees is a half, and you can't remember. Is there a way in your calculator you could solve sine of theta equals a half? Well, we undo it. So what operation undoes sine? Well, it'd be inverse sine. I'm going to show the work. It's really important that you understand what you're actually doing here. If you take the inverse on each side of sine, it's like opposite operation, like squaring both sides or square rooting both sides. You're undoing it. On the left, we just have theta. On the right, that's where we do that inverse operation to get that angle measurement. So on your calculator, I want you to type that in. Pay close attention to your mode, though. We want to make sure that we're in degrees if that's what you want to work in, if that's easiest for you. So I'm going to do inverse sine of, I'm just going to say 0.5, it's a little bit faster for me. And you get 30. So great, that was our first one. So when is sine equal to a half? It was 30. But notice you're not getting the 150. Your calculator is programmed to do principal values only. So you're still going to have to know, oh yeah, sine's positive in quadrant 2. I need another answer. So keep that in mind. Now let's do the other one. Inverse sine of negative 1. What does it say? Negative 90. That's not the same as what I wrote down. I wrote down 270. Are those coterminal? 270 and negative 90? Well, sure they are. They're two names for the same location. So why is your calculator saying negative 90? Because that's the principal value. So when we have it on your calculator, it's going to do that one solution that we're all supposed to know with our limitation. Limitation for sine was negative 90 to 90. So you do have to be a little bit aware, cautious about what kinds of domains are you using when you give those answers. Okay, so strategy. Big important thing on this one. It was degree 2. We solved it by factoring. All right, so let's take a look at another algebra example. Again, I only want you to look at the algebra side to start with here. So I want you to take a look at the equation that I gave you and think strategy. If this was an algebra, what would you do? So I see all x's, so I have the same variable. What degree equation is that? Well, the degree is 2 again. So if it's degree 2, how do we solve those? Factor. So this strategy is so important. You need to have a plan. Factor. And again, your backup plan, you could do quadratic formula if you needed to. All right, so is this in a form right now that we like for factoring? Well, no. If it's factoring, we want to make sure it's equal to 0. So we're going to have to move some terms around. So I'm going to move the x to the other side. You could also move the 3x squared. Nothing wrong with that at all. I kind of like to have my highest degree term positive. That's just me. So set it equal to 0. Great, but this one only has 2 terms left now. It has a quadratic term and a linear term. So is it factorable? Maybe not in the same way the last one was. What do you always look for first when you're factoring? What could it have? Right? GCF. What could you pull out of both of those terms? Well, I can pull out an x. And then I have my 2 factors. I can set each of these equal to 0. I know the first one looks a little goofy to people, x equals 0, but that's what it is. X equals 0 is the value of x that would make that whole thing 0. And then our other one, 3x minus 1 equals 0. So x equals a third. So this is another parabola, degree 2, that would cross the x-axis in 2 places. We have 2 different real solutions. All right, so compare to the equation on the right, the trig equation. So does it look similar? Coefficient is 3. We have a squared term. It's equal to a linear term. Looks pretty much the same, but what's different? I replaced the x's with cosine. So I replaced the name of the function to a cosine. So it's basically the same thing. So it's a degree 2. So I'm going to solve it by factoring, which means the first thing I need to do is make it factoring ready equation here. So let's move that term to the other side. So I'm going to subtract the cosine of theta. Now, just like in the last one, in the algebra version, I'm going to factor it, but it's not a trinomial. There's no constant. I actually have a GCF. And in this one, the GCF is actually cosine of theta. All right, so I'm going to set each of those equal to 0 and solve. Those are my 2 factors. So when is cosine 0? And when is 3 cosine minus 1 equal to 0? So got to do some solving on that second one. And again, here's where we deviate a little bit from just regular algebra. In algebra, we would have been done. We had our 2 solutions, 0 and a third. In trig, I need to actually find the value of the angle that makes that true. So I need to think about what my restrictions are before I do this. So I'm going to restrict you again to 0 to 360. We're going to kind of keep working in that more comfortable domain of degrees here for a little bit. So when is cosine 0? When does that happen? So 90. And then, is there any other place, or is that it? Is there any other place that cosine is 0? Well, yeah, how about 270? So we got two places for that one. Remember, there could be more than one place. Doesn't have to be, but there could be. All right, when is cosine a third? As you're all panicking and looking at your unit circle, gosh, did I miss those? Is cosine ever 1/3 for a special value, special right triangle? Not something that I recognize. But is there an angle out there, maybe, where cosine is a third, where the adjacent side is a 1 and the hypotenuse is a 3? Probably. How are we going to figure that out? Well, we're going to do inverse cosine and see. So you're going to use your calculator. This is not a special value. There's no way for you to do it other than to use your calculator. So let's try it. We're going to do inverse cosine. Again, I'm going to stick with degrees here. And 1 divided by 3. And I got 70.5. Go ahead and round to tenths. We're not going to get exact answers, so we're a little bit limited there, but at least we have a guesstimate of what that would be. So 70.5 degrees. So thinking about a picture version of that, just so we're on the same page here with what we're talking about, the angle that you guys just came up with is 70.5 in quadrant 1. All right, so is that the only place where cosine would be equal to a third? Is that the only angle measurement? Is quadrant 1 the only place where cosine is positive? Or is there another quadrant? Well, yeah, there's another quadrant. Quadrant 1 and quadrant 4 are where cosine is positive. So we also have the same reference angle down in quadrant 4. We need to figure out the angle measurement that's 70.5 degrees away from the x in quadrant 4. It's no different than when we did 30 and 150 for that sine example. We had two places. Well, just like that, we have two places, but this is the angle that you need to figure out. I need to figure out how do I get to that place that's 70.5 degrees away from the x. Reference angle. Well, how about doing 360 minus 70.5, right? We need to figure out how far that angle is going around the unit circle, and we come up with 289.5 degrees. There's another location, and that's the part that can be kind of tricky. If you're doing just our restricted values, you'd only need the 70.5. But because this is 0 to 360, there could be another location where cosine has that value. So you have to think about reference angle and where those might be. All right, so bottom line, degree 2, we solve by factoring. So we look for those values that make the equation true. All right, now, not every equation has to be degree 2. So I want you to think back to most of what you solved in pre-algebra and algebra were degree 1 equations to the first degree. So like in my example here on the left, it's y to the first, single variable. What do? Well, you just solve, right? We do opposite operations and we solve. So here's your strategy. If it's a degree 1, we use opposite operations and you solve. So even if it's more complicated, like say you have to simplify each side of the equation first, or say you have variables on both sides, they're still the same degree. They're still to the first power. You can still solve. Just get everything on one side, numbers on one side, variable on the other, and we undo. So in this case, I'd add the square root of 3. I know that seems like kind of a goofy number for algebra, but it's not for trig, which is why I'm using it, and then divide by 2. I just solve. I undo what's been done to the variable. So y equals square root of 3 over 2. Solve for the variable. It's degree 1. Well, look at the equation on the right-hand side. It's the same thing, but in trig version. So instead of writing the y in there, I put sine of theta instead. It's to the first power. It's degree 1. We just have to undo what's been done to that equation. I do exactly the same thing. So I get the variable by itself. In this case, the variable is sine of theta to start with. So divide by 2. So I'm asking the question, sine of theta is equal to square root of 3 over 2. When does that happen? When is sine equal to square root of 3 over 2? So I'm going to limit again to 0 to 360. We'll talk about radians on this one too, though, just so you know what it would look like if you're going to say it in radians. But when in 0 to 360 is sine square root of 3 over 2? Well, reference angle would be 60. And what other quadrant besides quadrant 1 is sine positive in? Sine is the y, would also be in quadrant 2. So you need the 60-degree reference angle that's in quadrant 2. That would be 120 degrees. So I have two values. Now, what if you wanted to do this in radians? So I'm just going to say or. If you're going to do it in radians, I would say, well, what's 60 degrees in radians? Pi over 3. And then 120 would be 2 pi over 3. You need 2 of those to make 120. So you can always write your answer in radians as well. I think for a lot of people, they like to think about degrees because it's a little bit easier for them to remember. So in algebra, if it's degree 1, just solve for it. And we have those same things happening in trig as well. Okay, what we're going to finish up today with is what if what if they're not ready to be solved as an algebra equation? In trig, we have that kind of extra layer, and sometimes it happens in algebra too, or algebra also. Some other things we need to check for. So here's a couple reminders. I need you to check a couple things before you start solving. I need you to check your functions. What functions are being used? And then I need you to check your angle measurements. What angles are being used when we solve? So in this one, when I check my functions, I see the function cosine and I see the function sine. Those are different. They're not like terms. I would not be able to put them together. Let's check our angles. I see a 2x and I see an x. Again, they are not the same. I would not be able to put them together. So because my functions and angles are different, I'm kind of stuck the way it's written right now. I can't employ those algebra strategies that I know unless I do a trig substitution, which is hence the name in the big box at the top. We can try to substitute to make them the same. So see if there's anything on your pink sheet that can help you. Not a whole lot you can do for sine of x other than 1 over cosecant. Not super helpful. But I'm guessing that we can probably do something for this. Now, if you look at your pink sheet, there's 3 different options. Always harder sometimes when we have choice because they all work, but there might be one that's significantly easier to use than the others. So take a look at what's on the other side. Look at your pink sheet. Pause the video if you need to. What would be your best option? All right, so this is the one I selected, and let's talk about why that might be. Why do you think I picked the one that I did? Well, uses the same function name now. They're both in sine, and they both have the same variable. We're shooting for getting it into a point that we can solve it algebraically, so I can definitely solve this now. So what degree is it? Well, this is degree 2, right? So we go back to asking ourselves all those questions. If it's degree 2, you want a factor. If you want a factor, you want your equation equal to 0. So let's do that. Let's get that equation equal to 0. I'm going to move that negative 2 sine squared to the right-hand side. I know that seems crazy to people, but you can have variables on the right. I just want it to be positive. I like that better. And then I'm also going to move the 1's over there. But when you move the 1's, on the left-hand side, we have just 0 then. And on the right-hand side, that's 0 for those 1's as well. So we have no constant term at all. All right, so it's degree 2. I have my equation equal to 0. I am ready to factor. So no constant. So this one, I can pull out a GCF. So don't forget to look for that. Some people forget GCF. They think it doesn't factor, but we can definitely do GCF. Set each of those equal to 0 and solve. All right, so we're looking at what makes sine of x equal a half and what makes sine of x equal to 0. And again, I've imposed the same limitation on you here. So when is sine 0? Well, that happens at 0 and at 180. So again, there's more than one place. And when is sine a half? That happens at 30 and 150, quadrant 1 and quadrant 2. So it's remembering that unit circle and where those are going to be happening. So the moral to this one, the angles weren't the same and the functions weren't the same. So sometimes we have to do a trig substitution first, not unlike what we did in simplifying and verifying. Sometimes you already have like terms. Sometimes you don't, and you have to substitute. Okay, so the last one we're going to do for this part 1 to finish this up, then we'll do lots more strategies tomorrow and more practice with that, is one more like what we just talked about. Kind of start to finish, what would you do? So check your functions and check your angles. We're cool on functions. They're both cosine. Fantastic. Check your angles. One of them's a 2x, the other one's an x. We're in trouble. I can't put those together. They're not like terms. I would never be able to do that. So I'm going to have to substitute. There's no way to make this the same unless I substitute. So take a look at your pink sheet and see which one you want to substitute for. Cosine of x, you don't have a lot of options, right? 1 over secant, not super helpful. So I'm guessing it's probably going to be this. So take a look, see what we can substitute for that. All right, well, you had 3 choices again. I'm hoping the one that you came to was this one, because that's going to give you everything in cosine. So again, your goal is to try to make them all the same. Now, I wrote it without a very critical piece that I should have when I make that substitution, and hopefully you did it So I could talk about that. So parentheses, gotta have them because there's a 3 out front, right? You're gonna multiply 3 times everything on the inside. If the 3 weren't there, I really wouldn't have to worry about it as much, but it is, so I need to take that into consideration when I simplify. Okay, so now I can do algebra, right? Because everything's cosine and everything's x. So now we're back to thinking about what algebraic strategy is gonna be the best for us. So think about degree. What degree is this equation? Well, it's degree 2, which means what are you going to do? Factor, if it works, otherwise quadratic formula. But in order to do either of those, the equation has to be equal to 0 first. So does this look like you want it to? No, we got a mess. So what kinds of things would you do? How about distribute? So 6 cosine squared minus 3. If you forgot those parentheses, guaranteed you'd mess that up. All right, now it's not equal to 0 either, so let's move the 2 over. What are you going to subtract the 2 from on the other side? The 3. If I'm going to look for errors in this question, I'm going to look right there because most likely that's what you're going to mess up. Cosine would come next if we're going to factor, right? We want descending order, highest degree term down to the lowest. What would your constant be? 5. Okay, now is there a GCF? Nope. So we're going to try to factor it into 2 binomials. So for the factoring, again, you have to think about what multiplies to give you 6 cosine squared. Well, it could be 2 times 3, or it could be 6 times 1. I think the pair that we want is the 6 and the 1. We want the last term to be a minus 5. The only thing that can do that is a 1 and a 5. It's a negative, so that means we want one of each, so a positive and a negative. And I think the way we want that to work, because we want it positive in the middle, is we want this. Outsides would give you positive 6, insides would give you negative 5, and positive 6 plus negative 5 adds to the 1. So you have to be able to factor those. Now set them each equal to 0 and solve. Oops, I'm already solving here. I know a lot of you do that too, and that's fine as long as you know what you're doing with that. So when is cosine equal to negative 1? And when is cosine of x equal to 5 over 6? Let's do the negative 1 first. That might look more familiar. When is cosine negative 1? That happens at 180 degrees. So again, we're limited 0 to 360. For the other one, though, when is it 5 over 6? Gosh, that's not a special value angle. So how do we do that again? Well, you're going to need your calculator. We need to do inverse cosine of 5 divided by 6. All right, so we get 33.6 degrees. That's one location. Now you have to think about, is it possible that there's another one? You just did quadrant 1, so you did 33.6. I need to think about, is cosine positive anywhere else? Well, sure it is. It's positive down in quadrant 4. So we need to represent the angle that has that same reference angle. That's 33.6 degrees away in quadrant 4. So I need that angle right there. So 360 minus 33.6. which would give us 324.4 degrees. Don't forget about your other possibilities. So factoring is a great way to solve, but we can't factor unless we have all the same function and the same angle. So trig substitutions are going to play a big part of our simplifying before we can solve. All right, so that's kind of our part 1. We'll do more examples in part 2.